Hi everybody. Today we're going to be looking at the Munkres Assignment Algorithm, also known as the Hungarian Algorithm. The basic idea for this algorithm is simple. We're given n people and n tasks, and a cost for each person to do each task. We want to assign each person to their own task one-to-one so that we minimize the total cost. We assume that all costs are positive real numbers and that the problem has a unique solution. If those are both true, then we can use this algorithm to find that solution. We'll show how the algorithm actually works with an example. Let's say we have 5 people: Anna, Bill, Charlie, Dan, and Emily, and 5 jobs, which we'll creatively call Job 1, Job 2, Job 3, Job 4, and Job 5. We also have a cost associated with each person taking each job. We want to assign each person to their own job, so we have the lowest possible total cost. The first step is to put our example into a square matrix. So here's the matrix representation of our people and jobs. Next, we do row reductions. Find the lowest item in each row, and then subtract every item in that row by that amount. As you can see, that leaves at least one zero in every row, but not in every column. To fix that, we do column reductions on the columns, or in this case column, that don't have any zeros. The process is exactly the same. Find the lowest item and subtract that from every value in the column. We now have at least one zero in every row and every column. The next step is to provisionally assign as many jobs to people as possible. We do this by finding rows with only one zero. So for Anna, it's job 3. We then cross out every other zero in that column, as that person has been assigned that job. We have several zeros in Bill's row, so we leave that for later. And we assign Charlie to job 2. For Dan and Emily, there are now no uncrossed zeros in their rows, so they can't be assigned to anything. Now we go back to Bill. As there are several uncrossed zeros in his row, we start looking at columns instead, matching the jobs to the people instead of the people to the jobs. We start with job 1, and we see there's only one zero in Bill's row, so we assign it. We'd repeat these steps until there are no uncrossed or unassigned zeros. Now we have to assign the ticks. To do this, we firstly tick any rows without assignments. So Dan and Emily's rows get ticked. Next, we tick any columns with zeros in the ticked rows. In this case, both our ticked rows, Dan and Emily's, have a 0 in column 3, so we tick that column. Finally, we tick any rows that now have assignments in ticked columns. In this case, this only applies to Anna's row, because it has an assignment in the now marked column 3. So we tick Anna's row. Now we cross out any unmarked rows and marked columns. What we've done here is cross out all the zeros with the smallest possible number of lines. Now, from what's left, we find the smallest element. In this case, it's the 1 in Emily's row for job 5. This becomes delta. We now reduce every uncrossed element by our new delta. We now find every element crossed twice, so in this case, the 0 in Bill's row in column 3, and the 3 in Charlie's row also in column 3, and we increase them by delta. We now have a new 0 in Emily's row where the 1 was. We now repeat the process, assigning people to jobs if there is a single 0 in their row and crossing out any others in that column. And the same for the columns, repeating until there are no zeros which are unassigned or uncrossed. We now tick any rows with no assignments, any columns with zeros where ticks are, and now any rows with assignments in ticked columns, and cross out unticked rows and ticked columns. Now we find the smallest element left not crossed out, in this case the 4 in Anna's row, column 1, although we could have picked any of the other 4s with exactly the same result. And we call that delta. We then subtract everything not crossed out by delta, and add delta to everything crossed out twice. So we have this matrix. And again, we assign people to jobs if there's a single 0 in their row, and cross out any others in that column. Repeat this for columns, crossing out any other zeros in their rows, and repeat this process until there are no uncrossed or unassigned zeros. And we're done. So Anna has job 1, Bill has job 4, Charlie has job 2, Dan has job 3, and Emily has job 5. If we go back to our original table, we can see the original costs of each person with each job, and we can see that the total is 33, the lowest possible. So how can we be sure this algorithm actually gets a result? Well, first of all, the number of assigned jobs cannot decrease after each iteration, as we only ever increase our possibilities for assignment, as every new iteration creates at least one new zero in the matrix. Although this new zero might not immediately allow for a new assignment, repeated iterations will always allow us to find the solution. So let's talk about time complexity. If we let n be the number of people, which is the same as the number of jobs, the time complexity is big O of n to the 4. The row and column reductions can both be done in big O of n squared, and in the worst case scenario, we start by assigning only one job to one person and only ever increase the number of jobs assigned by one at a time. The maximum number of iterations and the cost of assignment depend on each other, and in the worst case, they take big O of n cubed time each. Hence the total time complexity is big O of n times n cubed, which is big O of n to the 4. Thanks for watching, and we hope this video helped you understand the Munkres Assignment Algorithm. Bye!